In the last video, we established another property that primes have, and that is the following. So if you take a number A, if your number is n that you're trying to decide if it's prime or composite, and if your number is A, and A is 1 mod n, then if you take its square root, for prime numbers, the square root has to be 1 or n minus 1 when you mod it by n. So if it's ever not, then you know your number is composite. So this is a property that partially separates primes from composites. So how do we use that in our primality test? How do we now upgrade our Carmichael test so to use this and make our Carmichael test better? Because of course right now our Carmichael test is failing on, well, on the Carmichael numbers. Okay, so the idea is, well, what we'll do is first we'll start with the Carmichael test. So for each A, we'll check that A to the n is congruent to A mod n. And of course, if that fails, we know we have a composite number. But if that passes, then what we'll do is, the first step is actually if you divide both sides of this by A, so A to the n divided by A is A to the n minus 1, and A divided by A is 1 mod n. So what I'm saying is that if this checks out, you sort of automatically have a number that is congruent to 1 mod n. And so now we can use this fact. Instead of A, though, it's A to the n minus 1. That's playing the role of A. And so take the square root of that. Take the square root of that A. Again, what we're calling A to the n minus 1. Take the square root of that. Well, if you take the square root of A to the n minus 1, so A to the n minus 1 to the 1/2, basically it's A to the n minus 1 over 2. And so you look at that, and if that's congruent to 1 or n minus 1 mod n, we're still in business. We might still have a prime. But if it's not, right, then this will tell us that it's that our n is definitely composite. So it's like an additional check for each A. We check this, and then we also check this. And actually, you'll see in the examples, if this guy is a 1, then we can do it again. We could take the square root again, assuming this is an even number, and see if that one is 1 or n minus 1. And you can keep going. So I'll show you that as in our examples. So 13 is 13 prime. Now we know it is, but a nice small number for us to test out how this would work. So first we would check, we start with 2, right? 2 is our first value for A, and we see if 2 to the 13 is congruent to 2 mod 13. So we look at 2 to the 13 and we mod by 13, and the answer is, it is 2. Okay, so check. But now what we do is, all right, so if 2 to the 13 is congruent to 2, then 2 to the 12 is congruent to 1. I'm just dividing both sides by 2. 2 to the 12 is congruent to 1. So I take the square root of 2 to the 12, and that's 2 to the 6th. And I want to see what 2 to the 6th is mod 13. And 2 to the 6th mod 13 is 12, which is n minus 1, right? So 13 minus 1 is 12. So that checks out. Okay, so then we could go to 3. Go to the next day. 3 to the 13, is that 3? 3 to the 13 mod 13 is 3. Yes, okay, check. So then we do 3 to the 6 and see what that is. 3 to the 6 mod 13 is 1. Now, because this one is 1 and this 6 is even, we can do another square root. We can go to 3 cubed. So there's like an additional check, another chance for this to fail and show that 13 is composite. So we do 3 to the 3rd. And it is 1. Now we stop there because I can't take another square root, right? 3 is not even, so this number is not a perfect square. It's 27, right? All right, but so we stop, we're done for 3, but that checks out. We go to 4, 4 to the 13. Mod 13, and we get 4. So again, our basic Fermat little theorem test checking out. But then our additional test now would be 4 to the 6. Again, I'm getting the 6 by doing 13 minus 1 is 12, and then cutting that in half. That's like taking the square root. So 4 to the 6th, mod 13 is 1. Because that's a 1, and this is even, I can go to 4 to the 3rd. I can take the square root again, and that better be 1 or 12. And in this case, it's 12. Okay, so that one checks out. And that's the idea. Now, I won't do all of them, right, because we know 13 is prime, so it's just going to continue to check off everything. But we would go all the way down to 12. And by the time we got there and did all these checks, we would be satisfied that it passed the test. Okay, and we knew it would because we know 13 is prime just from trial division. Okay, how about 2701? So we actually did this one in a previous video. 2701 will turn out to be composite. It's actually 37 times 73. And we found it using the Carmichael test. We got to the 5th one. This one actually ended up failing, if you recall. But let me just start from the beginning, pretend we didn't already do that work, and let's do this upgraded test. So first we would check 2 to the 2701 is congruent to 2, mod 2701. So 2 to the 2701, mod 2701 is 2. So that passed. But before moving on to 3 like we did last time, we'll do this square root idea. So 2 to the 2700, and then the square root of that would be 2 to the 1350. So let's do 2 to the 1350. And what we're looking for here is either 1 or n minus 1, which would be 2700. But we get 147. So that's a fail. So 2701 is composite. Now, as I said, this was an example that just the plain old Carmichael test catches by a equals 5. But you notice that we caught it actually earlier. We caught it on the very first a of a equals 2. Okay. Now, here's a good test. 561. This is a Carmichael number. This actually will pass all of the Fermat little theorem tests from 2 all the way up to 560. If all we did was that test, it would pass them all. But let's see if it passes our upgraded test. So let's pretend we're starting at the beginning and we do 2 to the 561 could grow into 2. Is that true? And the answer, I think, is going to be yes. Yep, 2. But before moving on to 3, we take away 1, 2 to the 560, and take the square root. So 2 to the 280, right? 2 to the 280. And we want to see if this is either 1 or 560. And we get 1. Okay, so we're still in the game. However, because this is a 1, we can actually do another square root because this is even. So we can try 2 to the 140. And here we get, 67. So that is a fail. So we now know that this is composite. And this is good news because this was a number that would have passed the Carmichael test if all we did was this row, right, 3, 4, 5, all the way up to 560, it would sneak past all of those tests and act like a prime the whole time, even though it was really composite. But now with our additional level of testing, we catch it. In fact, we catch it right at a equals 2. So that's a good sign. So we have caught a Carmichael number. So here's our test as it stands now. And we call this the Miller-Rabin test, named after two computer scientists / mathematicians who worked this out and included this second part. I know Miller is named Gary Miller, and I don't know Rabin's first name. And this, by the way, was developed just in the last generation. This is relatively new. This isn't like something that goes back to the 1800s. And it is just what we were doing. So for each a that goes from 2 to n minus 1, first we do the Fermat-Little theorem test, like the Carmichael test. We see if a to the n is congruent to a mod n. And then if it passes, we stick with that a, but we do a to the n minus 1 divided by 2 and see if that is 1 or n minus 1 when we mod by n. And like I said, sometimes you can go further. If this is 1 and this is still even, then you can do another square root. In other words, divide this by 2 again. And you can do that continually until you either get an odd number, so you can't take the square root, or you get n minus 1, which means you're not allowed to proceed anyway. So these are the tests that we do. All right, so that's where we are, and we're almost done. In one more video, I'll put the final touches on this. I'll tell you how well this test does. So the question, right? We just saw that this test caught a Carmichael number. Does it catch all Carmichael numbers? Is this actually the test we've been hoping for, that truly separates primes from composites? In other words, primes will always pass it and composites will always fail it, so that we don't get any false positives. So I will explain the situation in the next video.